we're going to start this afternoon's lectures by our second Best Poster Award that was awarded to Karan Mukhi from Oxford University. I think Jalal would like a picture, so so yeah, congratulations. Yeah, so he's going to present his work, and then we're going to have two more lectures, one by Spiros and one by Jalal, so our two DTU speakers. If you have questions for Karan or the speakers, I'll hand you the mic during the lectures. So yeah, you can start. Thank you.
Okay, hi everyone. Thanks for the interest in my work. So I'm Karan Mukhi, for those of you who I haven't met. I work in the control and verification group at Oxford with Alessandro Abate. And this is some work that I've been doing with him on distributionally robust methods for aggregating flexibility in populations of EVs. So as we go through the energy transition, system operators are going to have to operate their grids in more flexible ways to mitigate the intermittency in renewable generation. And alongside this, adoption of EVs and heat pumps is projected to accelerate significantly in the next decade, which is going to contribute to more congestion in the distribution networks. So populations of EVs present a lot of flexibility to the grid, and coordinating their consumption of energy could help mitigate some of the intermittency of renewable generation and alleviate some of the congestion in the distribution grids. So in this work, we consider an aggregator that has control over a population of EVs. And the aggregator is tasked with satisfying the charging requirements of all of the EVs in the population and providing as much utility to the system operator as possible. So this could take the form of having the aggregate demand of the population track a generation signal that mitigates the variability in some generation, or flattening some load profile to mitigate the congestion in the distribution networks. To do this, the aggregator should be able to characterize the aggregate flexibility in the populations that they control. And if the aggregator doesn't have complete knowledge of the charging requirements, then it would be good for them to have some form of uncertainty quantification over this flexibility. So just a quick outline of the problem formulation. We're going to assume that the aggregator knows the size of the population, the number of EVs that they control, and the distribution of the charging requirements that they are sampled from. So this distribution could be made up from historical data of charging requirements from the EVs. I'll define what I mean by charging requirements in a minute. And then from these two, we'd like to characterize sets of aggregate consumption profiles in which we have varying degrees of confidence in. So to do this, to derive these distributionally robust flexibility sets, first, I'm going to go over how to calculate and characterize the flexibility in a single EV, and then in a population where you know the charging requirements, and then I'll go over some methods to find flexibility sets with different confidence levels attached to them. So first, let's introduce our assumptions on charging. So we're going to look at this problem over a finite time horizon of t steps. We're going to assume EV consumption is constant in each time step, and so consumption profiles are piecewise constant. And finally, we're going to restrict ourselves to only charging, so no vehicle-to-grid operation. Okay. So the charging requirements of each EV. So this is what the aggregator will see when the EV comes and plugs into the grid and communicates with the aggregator. So they'll communicate these 5 parameters. The lower bound on required energy and the upper bound of required energy, and its arrival and departure times, the time steps in which they will arrive and depart, and then its power rating. And then we require that the EV is fully charged when it departs. And so we have the following energy and power requirements. So it can only charge when it is connected to the grid, and it can only charge up to its maximum power rating. So from this, we can characterize a set of consumption profiles the EV can take while satisfying these requirements. And it's quite trivial to show that it is a convex polytope. And I'll refer to this as the flexibility set of the EV. So just to be clear, in each dimension, it's the amount of power that the EV consumes in that time step. So I'm only showing 2 dimensions, 2 time steps here, but in general, these methods work for far more time steps. Now, given a population of EVs with distinct charging requirements, that they'll each have distinct flexibility sets. So can we characterize the set of all feasible aggregate charging profiles? Essentially, this amounts to adding every element of the individual flexibility sets together and then computing the result. So this is exactly the definition of the Minkowski sum. For those of you who don't know, it's just you take every element of 2 sets and then add them together and then compute the resulting set. So unfortunately, in general, computing Minkowski sums is NP hard. And ideally, we'd want to do this for large populations of EVs over long time horizons. So that translates to summing many high-dimensional polytopes, which in general is intractable. Because of this, prior work is focused on calculating inner and outer approximations of the Minkowski sum. But by definition, inner approximations don't contain all feasible sets, and so those methods are suboptimal, whilst outer approximations contain some infeasible sets. And so this may cause issues if the aggregators are required to track the aggregate consumption profiles that they say they will track. Okay, so but in this particular problem and in this particular framing of the charging requirements, there's some symmetry that we can leverage that does allow for a tractable computation of the exact Minkowski sum. And to understand this symmetry, it's nice to look at consider what each of the polytopes look like. Yeah, and for simplicity, and mostly because I had figures from a previous presentation, I'm sticking to like a fixed energy. So your lower bound and upper bound of energy is fixed. Okay, that's not working. So the power requirements constrain the polytope to lie within a cube with side length m, and the energy requirements. Oh, it's not working. Oh. The energy requirements constrain it to lie on a simplex with edge length e. So the resulting polytope is the intersection of the constraints, which is found at the edges where the edges of the cube intersect with the simplex. And so from this, you can see it should be easy to see that each of the vertices is made up from permuting the elements of the other vertices. Okay. And this is the definition of a class of polytopes known as Permutohedra. So you have one vertex, and then all of the other vertices are permutations of those elements. Okay? And there's like a nice intuitive interpretation of this in that like, if an EV is trying to minimize a cost, then they'll pick the vertex in which the ordering of the price in each time step is the same as the ordering of the magnitudes of the elements of these vertices. Now, Permutohedra have some nice properties that make them useful for computing the Minkowski sum. Number one, they're closed under Minkowski summation. So you sum two Permutohedra, the result is a Permutohedra, and they permit fast computation of the Minkowski sum. So this all allows us to compute the Minkowski sum quickly for arbitrarily large populations of EVs. And then we can relax this constraint that fixes the energy requirement to a single value, allow it to be within a set, and the result still holds. So we get a characterization of the aggregate flexibility set of our population. I'm not going to go into details of what mu is, but the key point is that there is a closed form expression of it, and it's quick to calculate for a given population. Okay, now we assume that charging requirements are not known by the aggregator, but are instead independent and identically distributed according to the distribution that we know, that is made up from historical data. Okay, so different populations will generate different aggregate flexibility sets. And so the best we can hope for is to characterize an aggregate flexibility set in which we have varying degrees of confidence in. So this set, we define it as the set in which with probability 1 minus beta, if we sample our population from the distribution, then the flexibility set that is generated by that will be, this distributionally robust flexibility set will be inside that set. Okay? So to do this, we can leverage this result to construct an ambiguity set over the set of possible sampled populations of EVs. So this result says that if we're sampling from this distribution n times, then the empirical distribution generated by that population will lie within a Wasserstein ball of radius epsilon with probability 1 minus beta. So if you guys don't know what a Wasserstein ball is, it's essentially the Wasserstein distance is a way of measuring distance between two probability measures. And then the ball is all probability measures that have a distance of less than epsilon centered around this original distribution. And then we get this nice expression from this theorem, we get a nice expression of beta, our confidence, that depends only on n and epsilon, and these two coefficients that can be derived from the distribution. Now, we can use this ambiguity set to construct our distributionally robust aggregate flexibility set. Okay, so to do that, we require that our robust set is a subset of all flexibility sets of populations generated by populations in this ambiguity set. Okay, and then essentially this is one way of visualizing it a bit better. And so our robust set is the intersection of all of the flexibility sets generated by populations in this ambiguity set. In practice, enumerating all sample populations in the ambiguity set is intractable. So instead, we can make some progress with this lemma that says there are two populations, two worst-case populations in the ambiguity set, such that the intersection of the two of them is the intersection of all flexibility sets within this ambiguity set. And so we only need to calculate these two flexibility sets to compute our robust flexibility set. And so taking the intersection of these two flexibility sets will yield a distributionally robust aggregate flexibility set that looks something like this. And then we can use all of this methodology to, will this work? Yes. Okay. We can use, like, an interesting corollary of this is we can use these techniques to sort of motivate the utility of aggregators. So intuitively, like, we know that increasing the size of our population will increase the confidence that we have that each aggregate consumption profile will be able to be tracked. So this work gives a method of quantifying this. So here we're constructing our robust sets with different size populations, and you can see that the utility that we get from each per EV grows as we increase the size of the population. Now onto, like, a brief note over applications for this. So this could be used to manage congestion on the distribution grids, and we could use it to bid uncertain flexibility into spot markets, or for more general flexibility markets. And yeah. Okay, so in conclusion, we've got a method of characterizing the exact flexibility in sets of the exact aggregate flexibility for arbitrarily large populations of EVs. And then we've provided methods for characterizing the uncertainty in each of these sets. Thank you for listening.
Thanks a lot, Karan. Very interesting. Any question to Karan? Yep.
Hi. How did you compute the L and the UN sets so that you can do the...
Yeah. So I didn't go into that, but essentially what you're doing is you take your distribution and then you project onto an endpoint empirical distribution, and then you're essentially trying to find the worst endpoint empirical distribution. So there's some properties of Permutohedra that you can use that state that certain ones of them will be subsets of all other ones. And then you essentially use that to inform how you push around this empirical distribution to create these worst case distributions.
Okay, and I guess this scales well with, like, large populations?
Yeah.
Okay.
Yeah, very well.
Thanks.
Yep. So now, wait.
Thank you. I have a question. Like, in this graph, to my knowledge, there are many constraints which are violating. Then its graph is coming. Like this picture, this space is coming, right? Like, there are many constraints which are violating. Then only this aggregation is coming up, right?
What do you mean by many constraints?
Can you explain how you are aggregating this EV flexibility? Like, as far as my knowledge, that there are many EVs you are considering in the network, and you are basically aggregating that, like. You were saying that in the starting, the Minkowski sum, right?
Yeah.
In which there's no network constraints you considered.
Yeah.
It's
So
just the addition.
We're using, like, a copper plate.
So is it just Minkowski summation, or you are considering the network constraint also.
So in the work that I've done, you don't consider any network constraints.
So you are not taking consideration of network.
No.
Okay.
But yeah, this is what I'm going to start
It's
looking
just
into.
Minkowski. Okay. And the next is, what is U1 and U2? What is x-axis and y-axis? Is it
So
active?
this is the power consumption in time step 1, then power consumption in time step 2. Okay. It's got nothing to do with, some people were thinking it was like active and reactive power. It's just active power in the first time step, active power in the second time step. Like the consumption of the EV in these 2 time steps.
Okay. Thank you.
Okay, yeah.
Okay, thank you.
What are the hypotheses that you need to make to be sure that you can approximate your set with only an upper and a valid?
So what are the assumptions you need to make?
To have only 2 sets that.
Yeah. Okay. So this is. Where was it? Yeah. This is only for EVs with homogeneous arrival and departure times, with the same arrival and departure time. So we can do this very well for homogeneous arrival and departure times. When you look at EVs that have different arrival and departure times, what you can do instead is you split up the, so you have a certain budget, this epsilon, your budget that you have to move around your empirical distribution. So you can split that up around your different groups of EVs with different arrival and departure times, and then spread the risk out amongst them, and then optimize for that. Optimize with that being a parameter, a variable in your optimization.
The epsilon here, it's the uncertainty on the energy needed for the EV, or
it's no, it's the it's the radius of your Wasserstein ball. So it's
sorry.
1 second. It's the radius of your Wasserstein ball. So it's got to do with how much confidence that you have that your charging constraints will lie within this ball. So your population, you say, lies within a ball around your original distribution, and then this epsilon sort of describes how far away from your original probability measure you can be.
Thank you.
Last question. Yeah.
Thank you.
Sorry, this is for a fixed time, no? The number of vehicles that are connected at a given time t, I guess.
So you say you have a fixed size of your population, but you're planning into the future without knowing all of these charging requirements.
The question is whether you can apply this for an expected probability of vehicles arriving in the future.
Yeah, it's a good question. I haven't considered that yet, but yeah, it's interesting.
Right.
So thank you so much, Karan. It was very great work. Thanks a lot.